This is Kosmographia, the Randall Carlson podcast. Welcome back, ladies and gentlemen. This is Kosmographia, the Randall Carlson podcast, and it has been a while for us since we've recorded an episode, but I think we're going to dive back into the climate change data. Meanwhile, we've been talking before the show started about how, what was it? It's been 10 years since the end of the world. Is that what we decided?
Yeah, we were.
We live in a post-apocalyptic age.
Yes, we calculated, we figured out that we were 10 years into the post-apocalyptic world now.
Right.
Yes.
Right.
With Solstice 2022, right? So 12, 21, 22 is 10 years after the turnover of the Maya calendar there.
Right.
December 21st, 2012, 10 years ago.
The Mayan apocalypse, right?
Yeah.
Weren't some people calling it that?
Yes. Think so.
Yeah, I remember that was a frustrating time for me because I was trying to make all the talk about, the 12-12. What were people calling it? 20. When all the buzz, I mean, it had some buzzwords.
Yeah, 12, 21, 12.
Yeah. I was trying to say.
Sorry, I was saying quell.
Well,
like try to chill the hysteria.
Yeah, trying to quell and say, look, it's very interesting. It's a very interesting date, but it don't mean the end of the world. The end of the world is a real possibility, but that ain't it.
Right. Calendars are circular.
Yeah.
So
new beginning.
Usually what happens is it just keeps going into the next circle. But no, I was on the internet telling everybody we were going to die. I mean, that was my favorite thing to do at the time. So
that was you.
Oh yeah, I was like, bro, this is it. Game over.
Were you being serious, or were you just liking to fuck with people?
Oh yeah, I was messing with people. But on the other hand, I had no idea. It was, who knows? I generally thought calendars are circular. Ours ends every year, right? So in general, I think if you have a very long calendar, when it ends, it just means you start counting the next one. But still, it was fun to sort of tell people like, no, bro, this is it. Game over. End of the world.
Here you are 10 years later, Russ.
Right.
Well, there were a lot of people heavily invested into the idea that it was going to be apocalypse.
Right.
There really was.
I wasn't, but we did host a fantastic, massive tinfoil hat party.
I think we stopped it.
Yeah, that's right.
Oh, that was
our
you guys.
party
So
may have
many
actually
tinfoil
stopped.
hats. It actually stopped.
We had a huge group of friends come up, and everybody wore crazy, awesome tinfoil hats they made, and we celebrated up at the top at our big house up there. Just in case the world ended, we were all good. We were up on top of a hill. We had water. We had fuel,
Plenty of beers.
tinfoil
Hats.
Yes,
Yep.
we had the hats. Yeah, so it was fun.
Mm-hmm. Well, so that. I mean, could be possible that you guys actually prevented the catastrophe through your.
That's right.
It is possible.
Look, if a butterfly flapping its wings in Bolivia can cause a hurricane, off the coast of Madrid, why not?
Yeah. Post hoc, right? That's what it is.
So
post hoc, ergo propter hoc, however it goes. The after, therefore, caused it. So, yeah.
Okay, so
so Solstice is solar still, right? And that's where we're at today. It's because it's southernmost or northernmost point.
Yeah, I mean, we are right at it. Kyle, while you're there, could you look up winter solstice Eastern Standard Time?
All right. While I'm here, I guess
you guys are Central Time, right?
While you're there,
Either one, you can adjust 1
we're
hour up
central.
or down, doesn't matter. Central time. Let's find out when the exact moment is, because I think we can pinpoint it to, because I don't think we're quite there yet, and it just
9:59 a.m. Wait, what does it say? No. Yeah, 4:48 p.m. Eastern for the Northern Hemisphere.
21 or 22.
22.
Okay, so tomorrow afternoon.
Coming tomorrow.
So we're almost there.
4:48 p.m.
From my perspective now, to my right is the south. Behind me is the west. So the sun is now over here. And it's been doing this for the last 3 months, going south, south. And it's kind of to that spot, and it's slowing down. We talked about this in the Friday night lecture I did with Robert and those guys. Coming south, stops, and now it's tomorrow afternoon. Well, it'll hang there. It's going to hang there. It takes
hang out there for a couple of days. Yeah,
it's going to hang out there for because it's just really slowing down. When you picture that horizon calendar of the sun, this is kind of how I did it. I held up do this here, something like this. So, okay, so to my south, to my north, and let's say this is the position on the horizon of the sun. And so this would be equinox, because straight behind me is west and straight in front of me. If I draw an alignment from the end of my nose to this hand right here, and I project that to the horizon, I'm pretty much due east. All right. So now for the last 3 months, 3 months ago, solstice. Okay, so yeah, it's been moving like this. Fall equinox was right here, September 21, 22, right in there. And now it's been going like this. And the other thing to picture is that as it's moving past the equinoxes, it's moving faster, and then it slows down, stops, hesitates, starts coming back, moving faster and faster, slows down. So here's summer solstice when the sun is rising. Well, of course, we're looking west here because west behind me. So this would actually be sunset. If I was going to be geographically accurate, I'd have to turn around. But so behind me is west. So we're talking, sunset here. Got it? So the interesting thing here is ancient cultures often had a festival, a tradition of celebrating the return of the light, the return of the sun, S-O-N, the return of the sun, which if you go the 22nd and you wait 2 or 3 days, you're right at Christmas. So there you have it. That astronomical origin is that event right there is what's behind Christmas. And this is what spawned all of these traditions that we find all over the world going back through history of the celebration of the return of the light. Unless, of course, you're in the southern hemisphere, then it's reversed, but it's the same concept. So it's very interesting because once you begin, we talked about Halloween, and we saw that Halloween had an astronomical correlation. We got into that extensively. People can still get that Halloween through lecture and presentation on how to. Because even though it's based on Halloween and uses Halloween as a point of departure for the whole discussion and presentation, nonetheless, the information in there is valid information beyond simply that day of Halloween, right? Because it gets into discussion of the motion of the heavens and meteor showers and all of this kind of stuff that's of interest in its own right. It's even more interesting, of course, when it's connected with Halloween. So then this thing I did Friday is kind of looking at Christmas and also the roots, the connections of Christmas with astronomical events. And then we'll do another one in April that's kind of based upon spring equinox, Easter, and that'll tie it in very nicely with the Holy Grail and the Christian connections between the Grail and the crucifixion and resurrection, which is what the whole celebration of Easter is ultimately based in. Of course, the mingling of the the Christian tradition, along with pretty obvious pagan elements in the celebration of Easter. So we'll do one of those coming up in April, and then that will kind of complete this trifecta of Halloween, Christmas, and Easter. Of course, there's other things obviously we could do, but in our Western culture, those are three big ones. Now, we could do actually a summer like a July 4th, because you know what the astronomical connection with July 4th is?
Not a clue.
Not a clue. Well, let me put it this way. It has to do with the heliacal rising of a certain star.
Is it? You're saying it's
Which
the
star
heliacal
is that?
rising of Sirius? Is that what it is? Sirius? No.
I
Pleiades?
tell you, we'll
Okay.
circle back next July 4th, and we'll
I
talk
didn't
about
think
it.
Sirius was then. Okay.
No, I'll just look it up.
Kyle's gonna find out right now.
You're not gonna wait
yeah, okay.
until July
Kyle
4th to find out what the heliacal rising
Kyle
star
will
is.
just look it up. Well, so, I mean, look, I've got my my Stellarium software here. I could actually open it and show you guys, but maybe we'll save that.
So this was another of Robert Dakota's Earth Origin series, right? You spoke at multiple times. So you did a
Yeah.
2+ hour lecture on Friday night. So
Yep.
that'll be available as a video on demand, that particular lecture about Christmas and the solstice times.
Yes, I think it should be. I haven't been over to HowTube today, but it should be up. And if it's not up, I'm going to have to get a big stick and beat Mike over the head with it. Not Mike,
Russ,
not
no,
our
by the
normal
time-
guy, Mike.
By the time this video gets produced and out, it'll be ready, and the link will be in the description as always. So we'll have it there, and then he may have the rest of the presenters also available as a whole package. You had Ben Van Kerkwig, right, from Uncharted X, who actually we just found out is going to be on Joe Rogan. That'll be excellent in January.
Yeah.
And then Dave Matheson also, that's been on several of our Contact at the Cabin and Scablands tours with us. Also William Henry, and who am I forgetting there, Randall? There was a series of people over the weekend. So anyway, we'll have the
George was
links.
there,
We'll
right?
have the links to those.
George
Yep.
Howard.
Yeah, that's right. George Howard. Yeah, I wasn't able to listen to all of them throughout the weekend, but yeah, it was a pretty good lineup, and those will all be available for video on demand now.
Yeah, there's some great, really good lectures and some concentrated information in there. Couldn't recommend it more, actually. Yeah, so winter solstice, we're coming up. We're impending, and so the connection between winter solstice and Christmas. What I would do is recommend, people can download. We'll be able to download all three. You can download the Halloween. You'll get that whole connection with the Pleiades, the astronomical basis of our Halloween celebration. And now we've got the Christmas. You'll be able to see the connections, the astronomical connections between the celebration, throughout history across the world for the return of the light and its connection with summer solstice. And I got it. There's a whole bunch of very interesting things in there. The origins, the Christmas tree and the reindeer, a lot of the things, the colors of Christmas, which of course are what, Russ? What are the colors? So the two colors primarily concerned with Christmas.
Red and green.
Red and green.
Yeah.
And where does that come from? You'll have to watch
I'll have to find out. Yeah.
You'll have to. There's a bunch of interesting stuff in there. Absolutely. So, talking about, the connections, with the tree of life. The Santa suit, conjunctions, Jupiter-Saturn conjunctions we're talking about in there. Ancient structures with winter solstice alignments. Yeah, we can look at a little bit of that this evening in a discussion of the great year once again. So why don't we dive right into that?
Yeah.
Sure.
So earlier we were discussing the idea of the great year, and we kind of jokingly, we go back to the winter solstice of 2012, right? And we remember a lot of silly stuff going on about the end of the world and all of that. There was people seriously invested in the idea that there was going to be, that this was the apocalypse. You know, winter solstice 2012 was going to be the apocalypse because it was the end of the Mayan calendar. And I, to tell you the truth, did not really follow all of the rationales. I didn't read any of the books that were written and published supposedly predicting apocalypse, the end of the world scenario, eschatological interpretations based upon, the winter solstice of that year and what it meant. What I tried to do was to show that, look, as it turns out, winter solstice of 2012 was a very interesting thing that happened. And it didn't mean the end of the world, obviously, unless there's been a delay factor involved that hasn't been taken into account yet, but which could be, considering some of the stuff that's going on. But anyways, we could get right in. Let me see if hopefully we won't get messed up here.
I mean, I saw all kinds of stuff, while you're looking or while you're setting up your slides there. I saw people talking about, there was rapture ideas, and then, like the new agey, like, we're going to be raised to the fifth dimension and other people are not. And just, there was all kinds of stuff going on. There was consciousness was going to change. Not everyone thought it was going to be a physical destruction of the planet. Some people thought it was going to be the end of the world in terms of the way civilization or the way people think, the way civilization works.
Mm-hmm.
So there was all kinds of stuff.
What is this?
Yeah, it was like a second whammy after, pretty sure it was 1987. You had like the harmonic convergence. That was something that was talked about in the Mayan book. So I think it was kind of a secondary event people thought was going to follow up that to, like you're saying, some advance into next dimension or another level of consciousness.
Yeah. I read the Celestine prophecy, right? Kind of talking about that stuff, raising vibrations.
Well, I thought that the way consciousness would be changed is if people actually rationally understood the astromechanics of the event.
Well, that's no fun. We just want like death and destruction or new vibrations or something. That's way easier.
You either you want one end or the other of the spectrum. Death and destruction on one end, or the rapture on the other end.
Right, that's right. Yeah.
Or
full on enlightenment.
Well, no, this is a little bit more pedestrian, I guess you could say, than that. But are we seeing this share screen?
Yeah,
sure.
Okay. So here's a guy sitting out there, and this is the cosmic cross. He's sitting at the center of the crossing of the equinoctial line and the solstitial line, right? And that's the big cross. Let's see if I can back up a little bit here. Yeah. So, all right. So here we go. This was a significance. The cosmic octave, origin of harmony. The duration of the Platonic year, which is about 25,920 years, represents the amount of time the axis of the Earth takes to describe a full circle. The vernal equinox, journeying through each of the signs of the zodiac in this time. The vernal equinox is the point at which the equator, which is at right angles to the Earth's axis, intersects the ecliptic or the zodiac. In other words, the vernal equinox is the position of the sun at the beginning of spring. Now it is to be found between Pisces and Aquarius. The vernal equinox takes an average of 2,160 years to travel through a sign of the zodiac. This period of time is known as an age. Presently, the age of Pisces is coming to an end, and Aquarius is beginning. Although if you look at actual star maps and you assume the present configuration of Pisces and Aries, it'll be another 300 or 400 years before the vernal equinox has actually moved into the star field that comprises Aquarius. Okay. Presently, the age of Pisces is coming to an end and Aquarius is beginning. It is not possible to state exactly when one age ends and the other begins, because the signs overlap to a certain extent. Moreover, there is no absolute 0 point in the zodiac. Fundamental idea right there that we were kind of getting into earlier.
But if you divide the circle into 30-degree sections, that's kind of, on average, because they're definitely not all the same size, the constellations.
Exactly. So there's the signs,
the ideal,
of
the ideal division of 12 30-degree sections of arc.
Yeah. So those would be the signs of the zodiac as compared to the constellations of the zodiac.
Yeah.
Signs are idealized 30-degree segments. But here's the point. Where do you hinge the idealized wheel of 12 segments, equal size segments? Where do you pin that to the actual zodiacal wheel, the plane of the celestial, the plane of the ecliptic? That's the question. Where do you pin those? Just like you can go, well, look at the day and night cycle. Well, there's a definite connection, of course, between astronomical phenomena, which is the rotation of the Earth on its axis. So basically what's happening is rotation is on its axis once, and the tropical day has that 0 point. And the 0 point is when the center of the Earth lines up with the center of the sun momentarily, and that would mark the beginning of a day. And then, of course, we have to link our clocks to that, which is why because that point is different for all the places on the surface of the Earth. But nonetheless, it's a point where the local meridian line, which is that line that would, if you link the center of the Earth to the center of the sun, it would pass through the local meridian, right? But then where is the cosmic meridian? Where is the meridian? Where is the cosmic meridian or meridian for the year? Well, it depends. Is it the sun or is it the star? Well, the sidereal year, that 0 point is going to be hinged or linked to a star. The tropical year or solar year, it's going to be linked to the sun.
To the sun, yeah.
And of course, that is going to be a longer year than the sidereal year. Why? Because in that time that the Earth has gone around and comes back to the same point relative to a star, the sun has moved ahead a little bit, see? So the Earth is actually playing a little bit of catch-up. And so that's why the solar year is going to be longer than the sidereal year by a little increment. But now, and it's interesting that January 2nd January 2nd is Earth's perihelion around the sun. So it's only one day off of being January 1st. And when you think about it, that would make sense as using that point. In other words, in the elliptical orbit of the Earth around the sun, there's that moment where it's the closest to the sun.
Yeah.
The perihelion. So it would make sense. And this we can measure that. We can determine that with a high degree of precision when that occurs. So that would make sense to use that as your 0 point, or the term we learned was fiducial, the fiducial point. The point. Kyle, what you found was interesting. Would you say that over again? What you found about the origins of that term?
Yes. So I was looking at, it reminded me of fidelity, right? Like fiducial or fiduciary. So the fiducial, I was just looking on a Brave browser. I don't use Google anymore, folks.
Oh.
It says fiducial is based on or relating to faith or trust.
Mm-hmm.
Another one is relating to or characteristic of a legal trust, fiduciary. So it's kind of similar. But 3, regarded or employed as a standard of reference, as in surveying. So it's like a fixed something you trust, a point where you trust and you can compare
And you fix that, right? And then that becomes your reference point,
right? A fixed point that you trust, and then you can base all of your other measurements and calculations off of that one point. Yeah,
right.
Yeah, and fidelity is similar. It's like the same word being used in different ways. Faithfulness to obligations, duties, or observances, or exact correspondence with fact or with a given quality, condition, or event. Accuracy.
So
it's
okay. So it all kind of fits together. So then the question, to try to phrase the question here in a digestible way, we can say that the alignment between the Earth's center, sun center, and the local meridian is a fiducial point, because we can measure that with accuracy every day. And that's something that's been done with a high degree of accuracy since ancient times, because you can do it with a stick in the ground and a circle around the stick. And it can actually be surprisingly precise. But obviously now with instrumentation, we can determine that point to, just mere fractions of a second, right? And so we've got that. We can say, okay, here's the beginning of a new day. We use the Greenwich meridian as the reference. So you have to pick some point on the surface of the Earth that you're going to say, okay, every 24 hours when this point returns to that alignment between Earth center and sun center and local meridian, that begins a new day. And that right now is the Greenwich meridian. Then in the case of the year, the solar year, the calendar isn't really precisely tied to a fiducial point. But I was suggesting that the perihelion passage of the Earth around the sun would be a logical fiducial point. And coincidentally, that day occurs on January 2nd, one day off of the first day of our new year.
And is that because that pattern is also revolving in some way, so that we're closer in a different time, slightly later time now than we were many thousands of years ago?
I would think probably
at least
so. I don't have any definite information on that, other than the fact that if the what are you going to use for the reference? Well, the reference should be the Earth's position with respect to the sun. There's always going to be a perihelion. There's some point in its elliptical orbit where it passes that. However, what is the third reference point? Because you have to have that third reference point. And that would have to be a star or something on that level, because the stars are like the ultimate reference frame, the celestial reference frame, because from the human standpoint, they're not moving. Although, yes, there's proper motion of stars, and we can identify and measure that proper motion of stars. But from the standpoint of our human day-to-day experience, year-to-year experience, lifetime experience, the stars haven't moved much. If you live to be 80 years old, the heavens look pretty much, the day you die as they did the day you were born. Absent a supernova or a comet or something like that. As far as changes in the position of the stars, no, you're not going to see that in a lifetime. That's why we say the fixed stars. So the fixed stars is the ultimate fixed backdrop against which we measure all cosmic motion. Okay, but so what I'm saying is that our calendar is kind of free floating, but it's so closely aligned with a significant point that I wonder if it's coincidental, or somewhere along the line there was a conscious intent to tie the calendar and the annual cycle, the year cycle, which again, we know that the year cycle, we can define the year cycle to a very, very precise length of time that it takes to go around the sun and line up again, right? But what we don't really have necessarily is that 0 point within that. We can take that annual wheel, determine its span of time very precisely, but where's the 0 point on that clock?
Yeah, and you're suggesting that one possibility is the closest approach.
The perihelion, yeah.
So you have this astronomical cycle. It's a big circle, but you need to find a place to say here's where it starts and also ends. And so you look for some other astronomical event within the cycle, and you're saying one of them is where it's closest approach to the parent body.
Yeah.
The sun. Yeah.
That's it, exactly.
Right.
And what we see is when we look at the ancient monuments, well, with a high degree of accuracy, they were able to determine when these key points were within that cycle of the seasons, the cycle of the year.
Yeah.
And they did. And I mean, we can see all over the world that they use their henges, their stone circles, their temples, it's cathedrals, always had these alignments in them. So, whether it's, they say Fort Ancient in Ohio had a winter solstice alignment. So each year you could now measure the length of the year using relatively primitive pre-technological means by having, stones in the ground or having a passage way into a mound that lines up with that direction to the horizon where you get the equinoxes or the solstices. But now you have a means of determining the length of the annual cycle to a high degree of precision. Like at Newgrange in Ireland, and I could pull up a picture of it here, and I think I will in a minute. On winter solstice, when that sun gets to that farthest northern or southernmost point on the horizon, only on that day does the shaft of light penetrate the passageway into Newgrange and illuminate what was probably once an altar or some effigy or something that would have been in the middle of the sacred space within the temple, and it would be illuminated for a few moments. And now okay, the cycle has a distinct point at which you can anchor your thinking. Okay, here we go. We've got it. Now, you could do that just by observing things around you, almost like more of a natural or an unorganized, just by having key rocks lined up with a something on the horizon. You could tell within the day, without any great effort, if you were observant. But what we see in the architecture and the alignments there is that it's carrying that process to just a really high degree of precision, much higher than you would need, say, for normal, even if it was agricultural activities, if you were you were nomads and you were following the herds with the change of the seasons, and you knew that that was now the time has come that we have to break camp and get ready to start moving for the season. Yeah, you're going to know that within a few days, just by watching the natural phenomena, maybe aided by a few stones or sticks set into the ground. You don't need to build a huge mound with a passage in it that will tell you the moment of winter solstice to within seconds. You don't need that. So then that raises a question in my mind of, why do we find such a consistent motive to do this, widespread all over the world? While interestingly, the critics of the Netflix series say things like, well, we don't find any evidence of global connectivity. And that may be true as far as what we're able to discern once we pass the veil that separates the Holocene from the Pleistocene, that separates the Neolithic from the Paleolithic. Right? But we can also see evidence that the traditions of trying to link earth and sky together in this fashion are much older than the span of recorded history. And if that's true, then we've got to ask the question, well, how far back does this go? At what point do we begin to see that humans had this kind of working knowledge of cosmic motion and cosmic time and cosmic geometry? And that's the question, a very legitimate question, that Graham and other researchers, and even what we're doing, raising those questions, because conventional academia doesn't have an explanation for that. They just ignore it. They ignore it. They pretend it doesn't exist. But it's there. If we go back 4,000, 5,000 years ago, we can see those earliest cultures of the Holocene, the mid-Holocene, are already making acutely accurate astronomical observations. Completely, and then to ask why, and then we begin to realize that it's also connected with a very sophisticated geometry It's also connected with a high degree of engineering skills. And you put all that together, and then you go, wait a second. Are we supposed to believe that this is just the natural activity of hunter-gatherers or subsistent farmers? Why would they be marshaling skill sets on this level? Highly accurate astronomical observations, a high degree of engineering skills. And their engineering skills had to be extraordinary. By whatever means, they were able to transport 50, 100, 200, 500, even 1,000-ton stones and assemble them into an architectural, into a building, a temple. Well, it's just like how anybody can think that there aren't questions that need to be posed and answered. And of course, I think what they're afraid of is what the potential answers are going to be. But in any case, let's circle back. I digressed a bit. We're talking about the fiducial point, right? So now one of the things we've talked about a lot in this series is the great year of the world, right? The great year of the world. And so the question that I was raising for decades ago when I'm first learning about all this, well, is there a fiducial point? Where is day one of the great year? That's my question. In order to try to get a context for understanding that, let's look back at the screen share. What are we seeing? Are we still seeing this guy?
Yeah, we're seeing a little diagram of this guy in his football field.
Okay, so here you can see the shifting positions of the sun on both the dawn, which is the rising of the sun over here, and sunset. So we got sunrise over here, sunset here. This cross defines the four seasons. And what you've got here is the sun rising during summer solstice, far to the north, right? Coming up high in the sky, going back down. This is the longest day of the year. And given that the rotational rate of the Earth hasn't changed, you can see that if the sun is in the sky over an arc this long, it's got to be a longer span of time coinciding to the length of the day. Go down here, and you got the winter solstice, and you can see the arc of that particular curve of the sun in the sky is probably only half as long as this one here. And then you've got two times each year where it's right here in the middle of the two. And those are your equinoxes. And here's what you see, rising due east. In each case, it reaches its highest point or apogee when it's due south. Now, this is all from the northern hemisphere. If you're listening from the southern hemisphere, all you have to do is reverse this.
Just flip the image upside down.
Just flip the image upside down, or look at it. You could stand on your head and look at it as well. That would probably work also. So you can see there and so every day you can picture, like, let's start here at summer solstice, and now we're going to fall equinox every day, roughly 90 days, then another 90 days. And here's where we are right now, winter solstice. And within a couple of days, tomorrow, it hits that southerlymost point. And then
I thought it was today.
Well, it's still I think it's the 22nd.
It's 21st.
You said
Yeah,
22nd.
You looked it up. Isn't it tomorrow in the afternoon or something?
I thought it was.
It's wrong. It's today.
Oh, today
So
in
it's
the
past.
afternoon. We've passed it.
Yeah, it's past.
I thought so because
I'm sorry, guys. The first website I went to was bunk. Thank you, Brave browser.
So it's a done deal.
I went to Earth Sky, and that's where they had the more accurate one. And it is.
Okay. It was today.
Yeah, the first one said Wednesday, the 22nd.
Okay.
Sorry about that.
So it was okay. So you see, I suspected
think it was a typo
because I felt that the sun had actually stopped momentarily earlier this afternoon. I felt I was walking outside and I stopped and I go, okay, that's it. The sun has stopped. Okay. But then you told me that it's tomorrow. So I was thinking.
I'm sorry, guys.
It's today,
I thought the 21st.
I'm losing my superpowers as I get older here.
My fault.
Okay. So anyways, this is the yearly model. And this is a good place to start right here. Start between the Earth and the Sun. This is the flat Earth. Well, yeah, I mean, this is actually a NASA photograph. This is above. One other thing I'm going to call your attention to, the celestial North Pole. Now, that celestial North Pole is not fixed in space, is it? Why? Because as the Earth is doing this, there we go. I love this diagram. Because the Earth is spinning like a top. Its axis is forming. Let's see if I can do this like this. So that's what changes the tilt of the equator, which is the celestial equator, which is moving against the backdrop of fixed stars we were talking about earlier. And what that means is the point of intersection that we see right here between the celestial equator, which is the green circle, and the plane of the ecliptic, which is the orange circle. That intersection point is not fixed in space. It's moving. But we still use that as the fiducial point, that by which we can determine, okay, at the moment, and it's probably easier to determine the length of the year by reference to the equinoxes than it is the solstice, I would think, but maybe not. Probably at this day and age. But if you're just relying on visual, I don't know, maybe there's no difference. But in any case, you can set up foresights and backsights, and by using the horizon, you can get a hell of an accurate timing of when these four stations are crossed by the sun.
Weather's definitely better at the equinoxes.
This is true, yes. Yeah. So anyways, the point is on a year-to-year basis, this is shifting a little bit, but remember, we talked about this. Over the course of an average human lifespan, say of 72 years, the motion of that intersection there between celestial equator and plane of the ecliptic is 1 degree. And remember how to sort of guesstimate the arc of 1 degree in the sky relative to a human perspective down here on Earth? Well, that's a good one. The circle of the full moon is almost exactly a half a degree. 2 full moons is 1 degree. So that's about how much that intersection point, which is the vernal point, moves over the course of a human lifetime. And then when you figure 1 degree every 72 years, then you would go 30 times 72, and that's where you get the 2,160 years of an age, or what we could also call an astronomical month of the great year. So to go through the full circle and come back to where it is now, well, again, using the idealized, say, 72 years times 360 degrees, that's where we get our 25,900. Oh, I'm backwards. But you're seeing it right, aren't you? Right. So 25,920 years. So that's the idealized length of the great year precessional cycle. So the question is, what is the fiducial point that we could use as our trustworthy reference point to measure the starting and ending of a great year?
Could you use this would be kind of rough without like a really good telescopes, but like the dark rift in the Milky Way, so the center of the Milky Way galaxy, alignment with the sun on the equinox.
I think you're right on the money there, Kyle. Let's see if I can.
It wouldn't be exact, because that's not really an exact point unless you have a really good telescope. But
we can define that point with a high degree of accuracy relative to the length of the great year, 25,900 years.
Relative to the length.
And interestingly, in 2012, 2020, we were able to define that right down to the day. Right down to the day. And that's what made winter solstice significant in my mind. Let me see if, all right, so right here, well, let's see what we got going on here. So yellow line would be the plane of the ecliptic, and the green line tilted here is the plane of the galaxy.
Mm-hmm.
So what we're seeing here is the plane of the ecliptic and the plane of the galaxy cross right here. If you can you make out Sagittarius here?
Yeah. Right.
And over here is Scorpio. All right. So, and then you figure this is moving to the west. So at some point down the road, notice what's going to happen. Now, this isn't the exact center of the galaxy. In fact, you can see this is defined right, like you said, the black rift, Kyle.
The dark rift, yeah.
The dark rift, yeah. So, Kyle, you have earned yourself at least 3/4 of an attaboy. That was a good one. See, here it is right here. And so here's the galactic plane. And what you see is that this point is moving this way. And you can make out there's like if you picture a triangle here, and then you come down to where it meets the galactic center. You got that triangle? Well, in a few hundred years, this point here will be right there at the traditional tip of Sagittarius's arrow.
Oh, that's cool.
Isn't that cool? Yeah. So it sounds like almost it's a case that Sagittarius is drawing his bow and pointing it almost to the galactic center. Yeah, center of the galaxy.
I always use an asterism, which is the teapot, which is part of Sagittarius, but it looks roughly the shape of a teapot, and the spout, which I suppose is the tip of his arrow,
is
kind of pointing at the center of the galaxy. That's how I identify it in the sky.
Yeah. So this basically is a snapshot, a reconstruction of the sky on winter solstice 2012. So what you got here, imagine this would be from the vantage point of looking from Earth at the moment of winter solstice. So here you've got the sun and the Earth are aligned, where the sun is at the southernmost position in the sky. And you've got the alignment between the solstice position in the sky, the Earth, the sun, and basically the center of the galaxy. So this would happen every 25,920 years. The winter solstice will go around the circuit, come back, and you'll have that alignment, Earth, sun, galactic center. On that day, distinct day. Now,
Can I said make a correction. I'm sorry, but the teapot, I can see it now in your graphic here. The spout of the teapot is actually the knee of the horse, the front knee right there. That's the spout. That's that bright star there.
Which, look how close it is to the galactic center right there.
Yep, it's pointing right at it.
And I am not exactly sure how that's determined to be precisely the galactic. I presume it would be. And if I'm correct, there's a black hole right there.
Yeah.
Now that to me is very interesting. But here's the point I guess I'm getting at. This to me, the alignment with the galactic center, which is a distinct definable point in the sky that we can measure instrumentally, but we can also see visually, might be a very logical fiducial point to say the beginning of a precessional cycle, beginning of the great year. Now, what I'm thinking, though, is that because we're looking at 1/4 turn of the great year, what's coming up behind this in 6,400 years will be the vernal equinox. So if we had to pick and define a point, I would suggest the Earth, Sun, vernal equinox, galactic center alignment could be day one of the great year.
What do you mean? So not 6,480 years is the vernal equinox. You mean the equinox of the great year?
No, because this lined up on the solstice, the winter solstice. He's saying,
6,480 years ago would have been the equinox.
A quarter of a great year from now.
From now, yeah.
Gotcha.
Yep.
Does that make sense?
It does. So that means that 2012 actually marked us, say, if this is correct, 2012 marked us entering the winter of the great year.
That's one way of looking at it.
Yeah.
Yeah. Yep. So we kind of touched upon that a little bit in the Friday night. So, but there's a lot more in the Friday night. If people are, just because Christmas is past by the time you get this, there's a lot of really general good information in the presentation, just like there is with the Halloween. So don't go, oh, well, Christmas is over. There's nothing of interest here.
It will, in fact, happen again.
It will happen again. Right.
Yeah.
Exactly. Exactly. So,
well, should we take a break and then come back and get back into the climate stuff?
Let's do, because I want to talk about the thermal capture ability of carbon, and we'll look at that. I think that'd be a great place to come back to. Yeah.
Fantastic. All right. We'll be right back.
And welcome back, ladies and gentlemen, to Kosmographia. We are going to continue on this. I think we might be shifting gears now to talk more about the climate change stuff. But before we get into that, Randall, did you want to mention something about CBD from the gods?
Sure. I was mentioning to you before the break how, maybe 6 weeks ago, I was working out, trying to get back into a good routine. And unlike if I worked out 50 years ago, I kind of overdid it. And I really felt it in the joints of my elbows. Really, really tender elbows right there. So what I did was I kind of did a combination. I did the salve external, the oil internal, along with MSM, methyl sulfonol methane, which is basically sulfur, along with turmeric, curcumin, which is derived from. So that was kind of my regimen. So I think the combination of those things is, accelerated because, like I said, for about 2 weeks, I could hardly bend my elbows. And I'm going, oh, man, this sucks. But it's pretty much better now. So, and I think this combination of things maybe had a synergistic effect and kind of accelerated the healing process along. I may have left elbow. It may have been actually like tendonitis. You ever had tendonitis? Has ever had that?
Not sure.
Mike, have you ever had tendonitis?
Don't recall.
Oh, okay. Well, just forget about it then.
Nobody ever told me I had that.
Well, it's when your tendons are, if your tendons are hurt and you got tendonitis.
Okay.
Okay, so oftentimes it's been referred to as tennis elbow. You ever heard of tennis elbow? Okay, sure. So that's tendonitis generally. So anyhow, but it seemed to have helped a lot.
Can you get it from bowling?
I had pyramid legs a couple weeks ago.
Pyramid legs. Yeah.
Maybe that's
it's a bit of tendonitis.
Well, that's when you should have been lathering on the salve.
Okay.
Pyramid legs. Yeah, you guys did some crawling, didn't you?
We did.
Yeah. Anyhow, yeah. So I'd like to, I'll put in an endorsement. I use this product and I use this product in the outside and this product in the inside, combined with a couple of other things that are known to help really cartilage and joints and tendons and all of that. And I think it worked, at least for the time being, until the next time I overdo it, which could be any time. But so, yeah, the other thing I'll quickly mention to get it out of the way is that I've kind of made a commitment that every opportunity I get, I'm going to bring it up and remind people that on the Sacred Geometry International site, my work is being sold with no remuneration to me. It's been sold illegally by somebody who's been served 2 cease and desist letters, which he's ignored because apparently he's making too much money off of selling my work, I guess. But he was recently booted off of Bluehost because of copyright infringement, and he migrated everything over to an offshore internet hosting site, and then is continuing to sell my work, presumably thinking now he's immune. to the legal consequences of his actions. So I just want people to know that Sacred Geometry International is a fraudulent site. It's selling my work illegally, and it's going to be coming to an end very soon.
RandallCarlson.com.
I'll be get into that story.
That's the place, RandallCarlson.com. Everything legitimate, RandallCarlson.com, and anything you see connected with Brad or the Serpent Brothers, Grimerica, Ben Van Kerkwick, that's going to all be legitimate, because these are all good people that I've been working with, and I think my trust in these people is not misplaced at all.
And if you see anything from Normal Guy, it's bogus. I'm not anywhere.
Now, I have
normalguy.org.
In orbit.
Oh my God, we better go get those domains.
We better go check that
Go
domain
buy them right now.
Yeah, go to normalguy.org. Okay. Let me also say a few words of appreciation for Normal Guy Mike. It's been a pleasure knowing you, Mike, for 15 years now, you think?
15 or 20, something like that.
15 or 20, yeah. We've done a lot of business together with not a single shred of friction or conflict. It's been smooth sailing all the way through. The studio we built for Mike, that's how we got to know Mike. We built him a studio.
Great building. My wife loves it. It's her sewing room. It's her sanctuary.
We need to build you a man cave, Mike. You know, I don't think we've ever done an actual officially designated man cave.
What about the one you're sitting in?
Well, okay, I haven't thought of it that way, but now that you mention it,
look at that.
Look at this. My man, okay.
That's right.
Look, wow, okay. This is an epiphany for me, Mike, at this moment.
Well deserved.
Okay. I've done it. I've got a man cave. I've arrived.
Pretty bright for a cave.
Well, hey, look. All right. So check this out.
There you go.
That's my cave.
That's a proper man cave right there.
Yeah. Right.
Look at that bright pyramid in the middle there.
Got a pyramid in the middle of the table.
Yeah,
It needs a neon beer sign.
Yes. Yeah. Oh, we can do that.
Check this. Yeah, I've got a lot of creativity. I can control the light. Look at that. Is this awesome or what?
Truly awesome.
Very cave-like,
Truly.
for sure.
You need a ring light for your camera there, dude.
Nice.
We need to get you a ring light.
Okay, yeah. And then see on the back wall, I've got my wallpaper that looks like books.
I went into a place that sells like decorations for stores and whatnot, fixtures. They had rows and rows of just the spines of books, like the first 2 inches of books that they glued together and cut the backs off with bandsaw for decoration. They sold tons of these things for like athletes' houses and whoever.
Oh, that's hilarious.
It's just as decoration.
Jesus, what a contemptible practice. See, I made that as like a statement of derision and total contempt for the idea of somebody who would do that for decoration. But now you're telling me
it's real.
And in my imagination, I couldn't have even imagined that such a thing would be real. And now you are telling me.
They sell it by the foot.
Sell it by the foot.
Yeah, they get all these old books. They go to yard sales, whatever. They buy them and glue them together, bandsaw off the backs. And
so in the process, they are actually destroying real books.
Sure. Yeah.
Yep.
Oh, this is reprehensible.
It is.
We have to put a stop to this. This cannot be allowed to go on. This injustice will not stand.
Apparently it does in somebody's bookshelves.
Bandsawed books. I've never heard of that. That's interesting.
Oh, God. Anyhow, Let's talk about, because now that it's getting to be winter solstice, the cold weather is coming in again. The melting season for Northern Hemisphere ice is over now, and ice is growing again in the Northern Hemisphere. So I've always been interested in, the cryosphere. The cryosphere is the sphere amongst the set of environments in the earth. You've got the atmosphere, you've got the hydrosphere, the troposphere, the lithosphere, but you also have the cryosphere. Cryosphere is the realm of ice and snow. So I think I will do a screen share here. All right. Are we seeing?
Yep. Yeah, I see two articles there. Is that what that is?
Headlines. First one, December 12th, 2007. We were informed Arctic ice could be gone in 5 years. A lot of people were really in a panic over that.
How much of it?
And remember, no, all of it gone in 5. It could be gone in 5 years. Arctic ice could be gone, not diminished, not reduced in size, gone. Interesting. Notice 5 years. Add 5 years onto 2007, and we're right at 2012. So, Arctic ice was predicted to be gone by winter solstice 2012, which clearly would have fit right into apocalyptic scenarios, apocalyptic narratives. And then we see the following year in June, which is when the ice is actually at its minimum around August and September in the Northern Hemisphere. The North Pole may be free of ice for the first time in history, said Canadian climate scientist Dan Barber to CanWest News Service. This is a very dramatic change in the high Arctic climate system. And then we're informed in September of 2010 that the Arctic ice is in a death spiral. The carbon dioxide emissions from burning fossil fuels have melted the Arctic ice to its lowest volume since before the rise of human civilization, dangerously upsetting the energy balance of the entire planet, climate scientists are reporting. Yes. Who is this? Mark Serez, director of the National Snow and Ice Data Center in the U.S. city of Boulder, Colorado. The volume, extent, and thickness of the ice left in the Arctic likely reached the lowest ever level this month. I stand by my previous statements that the Arctic summer ice cover is in a death spiral. It's not going to recover. First of all, I can show that there's a mountain of evidence out there showing that there have been other times throughout the entire Holocene, there have been multiple times when sea ice has been reduced to the level that it is at now or less. And we'll save that. We'll get into that, dive into that, because it's really interesting stuff. But we will dive into that in a future podcast, absolutely, for sure. But so September 20, 2010, Arctic ice in a death spiral. So look at Arctic expert predicts the final collapse of sea ice within 4 years. So that would have been 2016, the final collapse of sea ice. It's done. No more. Sea ice is gone. It's collapsed. Boom. 2016. Then we come to 2014. They're bringing this back again. Arctic ice cap is in a death spiral. Let's see, when was the previous one? That was 2010. So 2014, they're resurrecting the death spiral. And of course, they've got the requisite polar bear.
Cute.
Yeah.
Yes.
Lovely polar bear.
Because now,
fluffy,
see, the deaths that poor. See, look at the expression of concern on the polar bear's face. You can tell he's worried.
As he's looking at the cameraman.
Yes. And going, say what? A death spiral? And then we come forward in a couple more years, 2016, and we've got Arctic could become ice-free for the first time in more than 100,000 years, claims leading scientist. He says we could predict that we could see an area of less than 1 million square kilometers for September of this year. That's a huge reduction in Arctic sea ice. Less than 1 million square kilometers. Well, here we are. Let's see. It's winter solstice 2022, about to turn 2023. What is the status of the Arctic sea ice anyway? We haven't been hearing a lot about that in the news lately. Have you guys been hearing anything about that in the news in the last few months?
No, it's definitely not gone.
If it was in a death spiral, I'm pretty sure.
I don't think it's gone. Well, let's take a look. The move. Arctic sea ice extent reaches 12-year mid-August high. This is from August of 2022, so this was a few months ago in August. Arctic sea ice extent reaches 12-year mid-August high. Now, what's significant about mid-August is that as it comes towards the end of the summer, we're getting into that period, that few weeks that represents the minimum ice extent throughout the course of the year before it starts growing again into cold winter months. Does that make sense? So, can't read the top.
And just to be clear, the sea ice obviously doesn't cover Greenland, right? But there's a portion of Greenland that is in the Arctic Circle.
Yes.
But not much. I don't have a globe right with me to show.
Right.
But yeah.
We're talking sea ice here. We're not talking about the Greenland continental ice. However, we should look at that too. We won't today, but we should look at that. So here's your Arctic sea ice extent. And if you look here, let's see what we got here. Over on the left, we've got the difference from the average in a percentage. And the average is the zero line coming right across here. And March, the dark text here coincides to the dark line. And that is the maximum Arctic ice. And what you see is that even though it's gone down, you see the September minimum. This was 2012. Well, that was the warmest. That was really the year that was all being proclaimed as the tipping point, because that was the smallest extent of Arctic ice since record keeping began. What they didn't talk about, though, because what they're trying to do is tie it into the concentration of carbon dioxide in the atmosphere. So they didn't really talk about the fact that there was a very powerful El Nino that year that disgorged a whole lot of heat. And it was basically a 1-year thing. And then the amount of minimum ice quickly rebounded after that, almost back up to the average. So the dark is the maximum. The blue is the minimum amount of ice each year. And this, you follow over to the extent here, you can see that this is the range in terms of percent deviation from the average. And that average is derived from looking at the amount of ice 1979 through 2022.
So the maximum isn't changing much, but the minimum has been changing quite a bit, and there is a downward trend in the minimum. Is that what we're looking at on this
That's
graph?
exactly what we're looking at.
Okay.
That's exactly what we're looking at. But when we go to this one, now here's your Arctic sea ice extent in the area of ocean with at least 15% of sea ice. And each of these curves, notice over here, extent, millions of square kilometers. Now, remember what that scientist that we quoted said, that it would be down to 1 million or less square kilometers. Okay, so notice where 1 million would be. Here's 2 million right here. So 1 million is down here. Now, this red dashed line, that represents that 2012 El Nino year. Okay, so let's take a look here. The red line, this red line represents the amount of ice right here in 2008. Okay, Now notice the blue line is 2022. So you'll see the blue line minimum is coming right in here, and it really is not different much at all, maybe even a little higher than the same minimum was back in 2008, which is what, 14 years ago, right? So, and then we can also look at the 2000. If you look closely, you'll see that there's this kind of smooth light blue line coming down here. See, here it is right here. Comes up, comes around right here, and it reaches the minimum, then starts going back up. So that light blue line is the 2011 through 2020 average, right? So the kind of wavy blue line in here, which we have more resolution of, and it hasn't been smoothed as much, which is above the average for the period from 2011 to 2020. That is the 2022 ice extent. So what we can say from this, here's one of the things we can say. We can say that in the last 14 years, or in the last, the light blue line is the average, yes. So in the last 14 years, the average amount, the ice, it's basically right up at what has been the average from 2011, I'm sorry, the 9 years from 2011 to 2020. So in other words, the minimum is less than it was 30 and 40 years ago, but it hasn't really changed since 2011. So in other words, we can say from this, for 11 years, the ice has not changed. It's where right now it is at the same place it was 11 years ago. That's how we could put it. So basically, all of these predictions here are completely off. You know, Arctic ice could be gone in 5 years. So the Arctic ice was supposed to be gone, according to this scientist here, this expert, by 2012. Here they're actually, this is June, right? So in June, they're saying, well, it could be, all the ice could be gone this summer. Well, that didn't happen. And then the September 20th, you know, Arctic into death spiral. And this is 12 years ago. So how's this death spiral worked out according to predictions? Well, if we had a death spiral, it was already in a death spiral 12 years ago. Shouldn't we see something a little bit less than the volume of ice that was there on average for the last decade? So this is June, again, June of 2016. This, I'd have to go through this, but yeah, as sea ice shrinks to record lows, Professor Peter Waldham warns a global disaster is now unfolding in northern latitudes.
Yeah, there's always this, what would you call it? Like,
wait, how does a global disaster only happen in the northern latitudes?
If it's global, it can't just be in the northern latitudes.
Sorry.
Yeah.
Go ahead.
But they always use this, this language, this, what would you call it? It's like inflammatory language, you know?
Yeah.
It's
Apocalyptic.
yeah.
Fear porn.
Right. It's definitely doom porn language, like final collapse, death spiral, you know, where it's always this, it's global disaster. I don't know. It seems unscientific.
Well, it is.
Yeah.
Right.
Fear,
and
fear.
This is the National Snow and Data Center in Boulder, Colorado, and they are not climate change deniers. But you can see right here, I mean, here is their own data. And you can see that 2012 was an anomaly. And it's come back up, and it looks like it's creeping up every year. So we'll have to see where the minimum is next year. But notice over here, when you're looking at the maximums, you know, pretty much right up there. They're all trending right there together. Look over here.
It shows that 2012 had a higher maximum and a lower minimum. It's just like it was at a year of extremes.
Yeah.
Like
Yes.
But they're also predicting that, right? Everything's getting more extreme.
That's right. Yeah.
Well, this is a function of El Nino, and this was a particularly potent El Nino that year. So it's the Pacific Ocean basically disgorging a whole bunch of accumulated heat. That's what El Nino is. So what we'll do here is look at a little research that was done. We'll start, if I can find it here, from years ago, early in the 20th century. All right, here we go. Found it. Okay, so this is from a 1913 study on volcanic dust and other factors in the production of climatic changes and their possible relation to ice ages. W.J. Humphreys, writing in the Journal of the Franklin Institute, which I presume is named for Benjamin. You've probably heard of Benjamin Franklin. Okay, so
been to the Franklin. We've been to the Institute too. It's got a great museum there.
Yeah. Wow, I'm impressed. You know, I'm not easily impressed.
Thank you. Yeah. Now I feel proud.
Okay. Just don't succumb to hubris.
All right.
It is true that carbon dioxide is more absorptive of terrestrial than of solar radiation. What does that mean?
Radiation coming from the Earth as opposed to coming from the sun.
Yeah, longer wave radiation as opposed to the short, fastly vibrating radiation coming from the sun. It is true that carbon dioxide is more absorptive of terrestrial than of solar radiations, and that it therefore produces a greenhouse or blanketing effect. And it is also probably true that it is the amount in the atmosphere, that its amount in the atmosphere has varied through appreciable ranges as a result of volcanic additions on the one hand, and of oceanic absorption and chemical combination on the other. And that chemical combination is going to be what happens when the ocean, well, it's always happening, but when the ocean cools, it draws down carbon dioxide out of the atmosphere, pulls it out of the atmosphere, and then it makes it available to biological life, algae and other things that, and shelled creatures that build their shells out of carbon in the ocean, which then becomes part of the limestone and dolomite bedrock and becomes sequestered away in the bedrock of the plain into the lithosphere, right? So we remember those statistics between the atmospheric reservoir of carbon dioxide, the oceanic reservoir of carbon dioxide. The lithosphere has major times greater amount of carbon dioxide locked up in the limestone rock than all the other reservoirs combined.
Right.
Okay, so that's what he's referring to there when he talks about the chemical combination. And that's what's locking up carbon dioxide. Now, if carbon dioxide was not being replenished, what would ultimately happen is the oceans would draw out the carbon dioxide from the atmosphere. And once it got down to 150 parts per million, the biosphere is gone. It's dead. It's history. And during the Ice Age, apparently it dipped as low as 180 parts per million. So it's only within 30 parts per million of causing the literal death of the biosphere.
Yeah, it collapses the food chain from the bottom, right?
Collapses it right from the bottom.
Yeah.
Absolutely.
There's the foundation out from the entire system.
Right. But it is not possible to say exactly how great an effect a given change in the amount of carbon dioxide in the atmosphere would have on the temperature of the Earth. However, by bringing a number of known facts to bear on the subject, it seems possible to reach approximate conclusions. Thus, from the experiments of Schleffer, we know that an atmospheric pressure, at atmospheric pressure, a column of carbon dioxide 50 centimeters long is ample for maximum absorption. Okay. Since one of this length absorbs quite as completely as does a column 200 centimeters long at the same density. What did that just say? It said between a column 50 inches, which under atmospheric pressure is going to absorb almost as much as a column 4 times greater. This is a very important.
Is this about saturation?
Yes, that's right. That's exactly right.
Okay, so 50 centimeters absorbs almost as much as 200 centimeters. That's what he was saying. And
yes.
Okay. Yeah.
In the laboratory. Now, the amount of carbon dioxide in the atmosphere is equivalent to a column of the gas at ordinary room temperature and atmospheric pressure of roughly 250 centimeters in length. Hence, according to the experiments just described of angstrom and EV bar, the carbon dioxide now in the atmosphere must absorb radiation very approximately as would a column 475 centimeters long of the pure gas at its average barometric pressure of, say, 400 millimeters. Now, to put it very simply, what it's saying, that if you had 250 centimeters in length, that amount is going to absorb as much as 475, almost double. In other words, turn it around. You got this much carbon dioxide, but half of that is still going to absorb as much as this.
Right.
But Scheffler's experiments above referred to show that such a column would be just as effective as 1, 2, or 3 times this length. And on the other hand, no more effective than a column 1/2 or 1/4 as long.
Okay, so the reason he's using column is because is it basically that if you take the entire height of the atmosphere and we know the parts per million, then you
think of it as the entire height of the atmosphere is a column.
Right. And basically the amount of carbon dioxide in any given section of that column of atmosphere is going to be about, what did he say, 200 and something centimeters?
Yeah.
Right. Okay.
It's absorptive. So in other words, 200, you doubled the length of that column.
Right.
But you're not absorbing any more hardly at all.
So if it was 800 ppm instead of 400 like it is now, it would be the same absorption just about.
Just about.
And he's saying that the 200 ppm or the 200 centimeter column absorbs almost the same amount as the 50 centimeter one.
Yes.
So even at 100 parts per million, roughly, it was basically having the same greenhouse effect as what we have right now at 400 parts per million.
Yes.
Okay.
And I got a graph I'm going to show in a second that will clarify that.
Okay.
So he says, hence, finally doubling or halving the amount of carbon dioxide now in the atmosphere. Since this would make but little difference in the total pressure, would not appreciably affect the amount of radiation actually absorbed by it, whether of terrestrial or of solar origin.
All right.
Again, as already explained by Abbott and Fowle, the water vapor always present in the atmosphere leaves because of its high coefficients of absorption. He's talking about water vapor now. In the atmosphere, which is absorbing heat at the same bands as carbon dioxide. In other words, the vibrational window of water vapor in the atmosphere is the same as the absorption bands for carbon dioxide. So he's saying here, as already explained by Abbott and Fowle, the water vapor always present in the atmosphere leaves because of its high coefficients of absorption in substantially the same regions where carbon dioxide is effective, but little radiation for the latter to take up. Leaves, but little radiation for the latter to take up.
Regions meaning regions of the electromagnetic spectrum? Is that what he's talking about? Regions of frequency of light?
No, I would say yes.
Okay, yeah.
In substantially the same regions, yes. The same regions of vibrational frequency.
Okay. Yeah.
I thought one portion of the absorption band of CO2 was outside of the water vapor absorption.
There's
like a little tiny sliver on the high end of this spectrum, I think it is.
There is. Yes, you're right. But not enough to appreciably affect to influence the overall effect.
Okay.
So hence, for this reason too, as well as for the one given above, either doubling or halving the present amount of carbon dioxide could alter but little the total amount of radiation actually absorbed by the atmosphere, and therefore seemingly could not appreciably change the average temperature of the Earth, or be at all effective in the production of marked climate changes. Now I'm going to jump ahead to a few years ago. Ed Hoskins is talking about this same thing. And I noticed that it's interesting that the climate crisis promoters always like to say, the function of carbon dioxide is well understood. It goes back to, Callender, Arrhenius, these guys, as if by saying that it somehow supports or bolsters their interpretation that we're on the verge of a climate crisis because of carbon dioxide. But I like to say, well, yeah, we've known a lot of things about carbon dioxide for 100 years now. Well, here's some of the stuff that we knew. We already knew the absorptive ability of carbon dioxide was logarithmic. That's what he's describing here. He's describing a logarithmic trend line. So we'll look at that in a second. So here's the effectiveness of CO2 as a greenhouse gas becomes ever more marginal with greater concentration. According to well-understood physical parameters, the effectiveness of CO2 as a greenhouse gas diminishes logarithmically with increasing concentration. And from the current level of 390 parts per million by volume, accordingly, only 5% of the effectiveness of CO2 as a greenhouse gas remains beyond the current level. This inconvenient fact is well understood in the climate science community. It can be accurately modeled using the MOD-TRAN program maintained and supported at the University of Chicago. The logarithmic diminution of the effect of CO2 is probably the reason why there was no runaway greenhouse warming from CO2 in earlier eons when CO2 levels were known to be at levels of more than several thousand parts per million by volume. Remarkably, IPCC published reports do actually acknowledge that the effective temperature increase caused by growing concentrations of CO2 in the atmosphere radically diminishes with increasing concentrations. The information is in their report. It is well disguised for any lay reader. It appears in Chapter 6 under the heading Radiative Forcing of Climate Change, Section 6.3.4, Total Well-Mixed Greenhouse Gas Forcing Estimate. So that's where you got to find their admission that this is true. The diminishing percentage effectiveness of CO2 as a greenhouse gas, as acknowledged by the IPCC, and its concomitant diminishing temperature effect are as follows. And we won't look at that right now at the moment because we're going to come back to this because we won't fully be able to talk about all of this in this concluding few minutes here. But accounting for the diminution effect, the diminishing effect, the actual temperature reductions achievable, the calculated achievable values are in the range of a few hundredths to a few thousandths of a degree centigrade. As the margin of error for temperature measurements is about 1.0 degrees centigrade. These minuscule levels, the temperature effects, for all the efforts of those nations attempting to control their CO2 emissions, are marginal, immeasurable, and thus irrelevant. These minute temperature changes have to be seen in the context of normal daily temperature variations at any single location of 10 degrees to 20 degrees centigrade. It can be as much as 40 degrees centigrade to 50 degrees centigrade over the course of a whole year. Although the IPCC tacitly acknowledges that this crucial diminishing effect with increasing concentration effects exists, it certainly does not go out of its way to emphasize it. Like the medieval warm period that they attempted to eliminate with the hockey stick graph in 2001, the panel knows that wide public knowledge of the diminishing effect with increasing CO2 concentration would be utterly detrimental to their primary message. And we're gonna look at a graph here. This is from a post by David Archibald on Anthony Watt's site back in 2010 on the logarithmic effect of carbon dioxide. So let me see. All right. Are we seeing the graphic of?
We are.
Good. It shows carbon dioxide's contribution to the whole greenhouse effect. So here we go. Down here, you got parts per million CO2, starting at 0 parts and ending at 1,200 parts per million. And over here, you've got the net downwards forcing in watts per square meter, which is just a measure of how much heat is being reflected back from the carbon dioxide in the atmosphere, how much is being reflected back of that longer radiation, how much of it is being reflected back towards the Earth, which, of course, is what is causing the heating, the global warming, right? Well, here you can see. So the blue is the forcing of the heat, the reflecting, think of it as the reflection of the heat back towards the Earth. That's the blue curve. So the red is carbon dioxide at the pre-industrial level of 280 parts, or what is this? They're going, 280 parts per million, right there. That's the red. Okay. The present is the green bar. So we've gone up, according to this curve, the heating effect of the carbon dioxide concentrations in the atmosphere has gone up a little measurable bit right here, right? And that's now. Then a doubling of which would be twice or a doubling of the pre-industrial is this curve, this line right here. So you can see what's happening is that
that's a difference in like what is 2.5 watts, maybe 3 watts total. Is that what we're looking at? Yeah,
that's what we're looking at.
Watts
that's what we're looking at.
Meter. Yeah,
and you can see, look in the first 100 parts per million. Yeah. That's where the maximum absorption takes place. That first 100. If we want to go, pre-industrial, you can see right here. Right, so this was the 280 parts per million. So 180 parts per million. You got to come down to here and draw a line up to about right there. That's where it was during the depths of the ice age, right there. I should add that line in just to show it. But here's what you can see is as the parts per million goes up, the increment of heating is diminishing in a reverse exponential curve or a logarithmic curve. We can go to the next one here. And this is, notice the Y range here is from 230 watts per square meter to 270. So you got a spread there, 40 watts per square meter. So they've taken a little narrow range of that spectrum and concentrated. Here you've got from 0 to, there's 250. So it looks about maybe 260 parts per million. And when you graph it that way, then look what happens to the curve. Look at this. There you can't even hardly detect a discernible difference in the amount of longer wave radiation being reflected back to the Earth between pre-industrial, and twice industrial. The way to see it is you gotta play with the range of.
You have to zoom in on that vertical scale there.
Yes, that's right. And then when you don't zoom in, this is what you get. So here you got 40 watts per meter, and here you got, a range of 260. But of course, you go to this one, and here what it's taking is the inverse by what it's showing is not the diminishing effect, but the increasing effect of the heat. So here you've got, look, here literally, okay, here's parts per million, right? So here's your 100 parts per million. Look at this. I mean, there's the first, so what do we got here? 20, 40, 60. So say by the first 30 parts per million, look at the amount of heat that it's capturing. And then look what happens to this curve in terms of the increase in heat with the heat capture with the increase in parts per million. So what happens when you're getting down here to 400 to 500 parts per million? The increase in heat capture is getting just minuscule. So, yeah, and then over here you've got degrees centigrade increase in atmospheric temperature per 20 parts per million increment of CO2. Degrees centigrade. So here you've got that in degrees centigrade with that first 30 parts per million. So here we got, like it says here, plant growth shuts down right there. Level during the ice age is right here. See at 180 parts per million. Here's your pre-industrial level, 280 parts per million. Here's your level in 2010, and here's your doubling of the pre-industrial level. So what effect is this having on the temperature of the atmosphere? As you move out here to these, the increments. So you can add an increment, but what's happening is you've got an inverse exponential increase in the heat. Now, that being the case, how in the world are they interpreting this, that the increase, I mean, isn't the idea that the increase in carbon dioxide is causing the greenhouse effect, and this is what's causing the heating, and this is what's causing the climate crisis?
Right, but what these graphs seem to be pointing out is that that we can't actually reduce carbon dioxide enough to stop the heating that they're talking about.
So how did their computer models then come up with the conclusion that this doubling of CO2 in the atmosphere is going to raise the planetary temperature by 2 to up to 8 degrees, I've seen?
Yeah. How
are they doing that? Well, that's the question we should be asking. And the answer is, and we'll dive into this deeper, the answer is that they insert a whole slew of positive feedbacks into their models in order to bypass what you're seeing right here. In other words, a small increment in the increase of the heat causes out of proportion changes in everything else that then feeds back into the system.
Right. Okay. Like some kind of chain reaction.
Yeah. And then here's the comment on it. Lo and behold, the first 20 parts per million accounts for over half of the heating effect to the pre-industrial level of 280 parts per million, by which time carbon dioxide is tuckered out as a greenhouse gas. One thing to bear in mind is that the atmospheric concentration of CO2 got down to 180 parts per million during the glacial periods of the Ice Age the Earth is currently in. The Holocene is an interglacial in the Ice Age that started 3 million years ago. Plant growth shuts down at 150 parts per million. So the Earth was within 30 parts per million of disaster. Terrestrial life came close to being wiped out by a lack of CO2 in the atmosphere. If plants were doing climate science instead of us humans, they would have a different opinion about what is a dangerous carbon dioxide level. Some of the IPCC climate models predict that temperature will rise up to 6 degrees centigrade as a consequence of the doubling of the pre-industrial level of 280 parts per million. So let's add that to the graph above and see what it looks like. Okay, so here's your graph above. We're going to add that 6-degree temperature centigrade that they were predicting onto this graph, and we'll see what it looks like. Okay, atmospheric degrees centigrade increases in atmosphere. See, they've had to change the y-axis to include a temperature change of 6 degrees. See that? How it's changed from here? Okay, good. Okay. Otherwise, it's the same data from just migrated over from the other graph. So degrees centigrade increase in atmospheric temperature per 20 parts per million increases of CO2. All right, so now let's see. Now, we know that naturally up to this point, that little mark right there, 280 parts per million, that's pre-industrial. So I think we can safely assume that prior to this, there's no anthropogenic effect. Okay. So now we're going to introduce the anthropogenic effect. And there we go. What the hell is that showing? Well, here's your pre-industrial level of heating. And here would be the predicted heating by 2010 based upon the increase of carbon dioxide in parts per million. And here would be this would be the cumulative warming for a 6-degree rise in temperature out to a doubling of the current of the pre-industrial amounts. So here's the heating, and then right here, boom, is this inflection point, and it just takes off, right? Is this realistic? Well, I mean, we're in 2022 right now, so we should be up 3 degrees warmer, 3 degrees warmer than we were in pre-industrial. Are we? The IPCC models of water vapor driven positive feedback is starting from the pre-industrial level. So the IPCC models water vapor, okay? Somehow the carbon dioxide below the pre-industrial level does not cause this water vapor driven positive feedback. If their water vapor feedback is a linear relationship with carbon dioxide, then we should have seen over 2 degrees of centigrade warming by now. We are told that the Earth warmed by 0.7 degrees centigrade over the 20th century. Where I live, Perth, Western Australia, missed out on a lot of that warming. So here we go. This is the natural heating effect of carbon dioxide is the blue bars, right? Same data, just plotted differently, right? Here's your atmospheric carbon dioxide. Here's your cumulative increase in atmospheric temperature, right? So here's that first 20 parts per million. And then you can see it's been tapering off so that every increase in carbon dioxide concentration incrementally is a exponentially less amount of heating unless you introduce the positive feedbacks of water vapor. So the natural heating effect of carbon dioxide is the blue bars you see right here, and the IPCC projected anthropogenic effect is the red bars. Each 20 part per million increment above 280 parts per million provides about 0.03 degrees centigrade of naturally occurring warming and 0.43 degrees centigrade of anthropogenic warming. That is a multiplier effect of over 13 times. So that's what they're doing. They're taking this, and right here at this point, they're using a multiplying effect more than 13 times the actual increment in order to generate this curve of anthropogenic warming, which was in the range that was predicted between 2 and 6 degrees by the end of the century. The whole AGW belief system is based upon positive water vapor feedback, starting from the pre-industrial level of 280 parts per million and not before. To paraphrase George Orwell, anthropogenic carbon dioxide molecules are more equal than the naturally occurring ones. Much, much more equal.
So the problem is actually not carbon dioxide, it's water vapor.
Well, no, the problem is not water vapor. That's purely a modeled process. In other words,
I was making a joke.
Oh, I see. Okay. I'm okay.
We don't need to control carbon dioxide. We need to control water vapor.
Yes, we need to get rid of water.
That's right. Okay. Yes. Well,
Carbon
you might
is
have
fine. Water is the problem, guys.
water is the problem. Right. Well, you can see
it's all that nasty dihydrogen oxide.
Okay.
Yeah. So his Orwell quote there that anthropogenic carbon dioxide is more equal than naturally occurring stuff.
Yes.
That's funny.
That's funny.
It's
but of
evil.
course,
The carbon dioxide that humans generate are mean.
Yeah.
They're evil. Yeah.
Even though it's exactly the same molecule.
Of course. Yeah. It's just.
Yeah. Yeah. If it comes out of a smokestack rather than a volcano, it's got 13 times more the heat capture ability.
Right.
I mean, that's basically what this assumption is doing if you take the worst case scenario of 6-degree warming by the end of the century, which is within their predicted range.
Yeah. Somehow it's linked there. I think the other thing he was trying to point out, correct me if I'm wrong, is that they're starting their water vapor calculations from that 280 parts per million
pre-industrial
right
levels.
In other words, they're not including like, well, this has been happening with before that as well, and you got to include that into the model so that you get a proper curve. They're not doing that. Yeah.
Right. All of a sudden, right there, that sudden little, if you go before 260 parts per million, right, there is no water vapor effect.
Right.
Yeah, there's no positive feedback from water vapor.
Right.
And then when you get to 280 parts per million, all of a sudden it just shoots off.
Right. Yeah.
So once again, it's just, taking a look and making an analysis of the whole of the science, and which they're counting on very few people doing. And that's how, they get away with what they're doing.
All right.
So anyhow, that's what I have to say about the matter.
All right. We shall wrap it up there for this week then.
I think so. I think that would be a good idea.
That'd be good.
Fantastic. So once again, ladies and gentlemen, randallcarlson.com is the website to go to. You can find information on tours, on Randall's upcoming events, lots of other stuff there. Also, HowTube. The videos get posted early on HowTube, so you can sign up there, get the videos early. Also, you can find it in the podcast. There is an RSS feed. Anything else, Brad? Any other announcements?
That's good. Quick coverage. That's
okay.
The big highlights we want to hit for sure.
Yeah, we got the tour coming up in the final third of the Cumberland Plateau trifecta coming up at the end of March, which I think is going to be a lot of fun. And it's going to be, I'm disappointed you guys are going to be in Peru. You won't be able to be there for that.
Turkey. Yeah.
Turkey. That's where you guys are going.
They're going
Turkey.
to Peru. I might be going. Wait a second.
Yeah, we got to go to Peru as well, but not this time. Yeah.
Yeah.
Yeah. Look at Göbekli Tepe, man. Got to go check that place out.
That's why I'm giving you guys permission to go.
Oh, okay. All right. Good.
Thanks, boss.
Well, hey, I try to be accommodating to, you guys.
The lowly employees.
Yeah, the lowly employees.
I saved up my attaboys. I'm out of here, bro.
So yeah, that sounds fun. But we will definitely also be having fun there. The lodge, the Cliffview Lodge. People go look up the Cliffview Lodge. We got that whole thing reserved for the last week in March, and we're going to use that as our base to see some of the stuff is really like a geological wonderland that's hidden. Most people don't go there in the winter and go, a little bit off the beaten path. Typically when the vacationers are there in the summer, you've got the thick canopy of vegetation. You don't see what's hiding.
Sometimes way off the beaten path. I think we got lost in the Middle Cumberland tour last time. That was fun. Well, I'm exaggerating a little bit. Yeah, remember we were on the trail and Rowan was like, which way are we supposed to go? And we wandered down this way, and we
that's
came back
right.
and yeah.
Because that's when we got back, and then we left, and we realized we were missing a couple of stragglers.
Yeah, well, I mean, I'm sure they were fine.
Did they ever show up, or what happened? Did we?
No one got lost.
No, just
we haven't lost anyone yet.
Just kidding, folks.
The Middle Cumberland tour was the Middle Cumberland tour was great. I wish I could go to this one too. I want to eventually go to the first one and also the third one, so I get to see all three. But I just can't do it this time. And I'm sure you guys are going to have a blast.
We are, and I'm sure it's going to be awesome going to Göbekli Tepe.
Yeah.
So who are you going with?
Ben.
Okay,
yeah.
Ben is. So has he been there?
I don't think so. We're going to Göbekli and Karahan Tepe. We're going to see Nimrut Dagi as well, and a couple of other sites. Yeah.
Okay,
it's
so
a lot of fun.
Before we should do this soon, like even this weekend. When I was hanging out with Malcolm, we were doing some Google research, and we were looking at Göbekli Tepe, and there is what appears to be some really large rock quarries, like 7 to 10 miles to the west of Göbekli Tepe.
Mm-hmm.
That might be something worth checking out and added to the itinerary. So we need to look.
I'm going to have to start running on that treadmill. I got to run 7 to 10 miles away from Göbekli Tepe to get there.
Through the hills.
Yeah, just.
Well, I'm wondering if.
Well, the people we're working with over there are familiar with the area, so maybe we can talk to them about it. See what happens. But this is the first time, this is our first time doing something over there, so we're going to be learning. It's going to be a big learning experience as well.
This is more of a recon trip, isn't it?
Well, no, we're taking people, yeah. So we do have people with us.
It's a small group, so it'll be.
Group, it's kind of a little bit of both.
Oh, okay. I mean, if you want to hang out for 1 second, I've almost got Google Earth open. I think you're going to be interested in looking at this. Unless you got to go.
I'm just saying, we can end the show and then you can show me.
Oh, right? Yeah, let's end the show.
Yeah, so good night, everyone.
Good night, everyone.
Merry
Christmas.
Night,
everyone. Merry Christmas to all of you. Happy holidays and all of that.